Today, we are going to discuss a very important numerical on steam and gas nozzles. The question is as follows. A steam nozzle, steam expands from 16 bar to 5 bar with initial temperature of 300 degrees Celsius and mass flow of 1 kg per second. Determine the throat and exit areas considering part 1 expansion to be frictionless and part 2 friction loss of 10% throughout the nozzle. So, now we'll discuss the given conditions. Inlet conditions are as given in the question. The inlet pressure is 16 bar and the initial temperature is 300 degrees Celsius. That means the entry of the nozzle is having 16 bar and 300 degrees Celsius, the pressure and temperature respectively. So this is the initial condition. Now from the steam table we have just read H1, S1 and V1. For this we'll have to see the superheated steam table at 16 bar and 300 degree Celsius. Then the outlet condition is given as 5 bar. The pressure is given as 5 bar. From the asked condition, which is the throat and exit areas, that means the nozzle which is being talked about is a convergent divergent nozzle, because throat is there in the convergent divergent nozzle only. So now we don't know the intermediate pressure which will exist at the throat of the convergent divergent nozzle. However, we are knowing the inlet pressure as well as the outlet pressure. So for the throat pressure, we'll have to find the intermediate pressure using the formula P2 by P1 is equal to 2 upon n plus 1 raised to the power n upon n minus 1. We have used this formula as the condition of discharge is not given in the question and nothing else is given about the intermediate pressure. So we are considering the condition for maximum mass flow rate, which is this, as we have derived this in the expression for maximum mass flow rate. As discussed in the derivation, that n is equal to 1.3 for the superheated steam. So putting n is equal to 1.3 and P1 is equal to 16, we get P2 is equal to 8.73 bar, which is the pressure at throat of the convergent divergent nozzle. So the three pressures are known now. As from the TS diagram, we can say that this top pressure inlet is 16 bar, this intermediate pressure is now 8.73 bar, and this bottom pressure, that means the exit pressure, is 5 bar. The initial condition is 300 degrees Celsius at 1, then it is till the point 2 it is the expansion in the till the throat, and then 2 to 3 is from the throat to this exit. Now as given in the question that the friction loss is taking place throughout the nozzle, as we have seen in the nozzle friction that in the convergent divergent nozzle the friction is negligible in this convergent portion, but here the friction is given to act in the whole area or whole flow of the nozzle. So this will also be considered, and hence this 1 to 2 dash is the deviation of the process in the convergent portion, and this 2 dash or 3 dash is the deviation in the divergent portion. So now to find the condition of steam at point 2 and 3, this is similar to the conditions found for the Rankine cycle processes in the turbine. So it has two processes or two methods which we can use for finding this. That is by the use of Mollier chart or by the use of steam table. As we are very fond of steam table, so I am discussing the method by using the steam table. Later on I can also discuss the method by using the Mollier chart. So for the steam table, what we do is, as we have already done it in the Rankine cycle, first we see the SG at the concerned pressure, that means at point 2. Point 2 the pressure is 8.73 bar. So we are finding SG, but SG will be found at 8.73 bar will be calculated using the interpolation method. So this is the value at 8.8 bar and this is the value at 8.6 bar, and we have divided it by 200 and multiplied it by 173, so that we get the value at the 8.73 bar. So this is a well-known method as we have used it multiple times. If you find any confusion in this interpolation, you can contact me. Fine. So this is the SG at 8.73 bar. Now we will compare this SG with the S1. So S1 is this. So that means S1 is 6.88 bar, which is equal to S2, which is 6.88 bar only. But the SG at this pressure is 6.63. That means the condition at point 2 is superheated. This already we have tried multiple times in the questions of Rankine cycle. So we have to now find the temperature of superheat at the point 2. So we will do S1 is equal to S2 and we will use the formula for the superheated for the entropy of superheated steam, which will be S is equal to Sg plus Cp of superheated steam into Ln upon T superheated upon T saturated. But the temperature of saturation at the condition, which is 8.73 bar, is not known. That also we have to find using the interpolation. So this is the interpolation and the saturation temperature at 8.73 bar is found to be this much. Now so now we know the superheated temperature, saturation temperature. So we will find the superheated temperature. Here we have taken Cp of superheated steam as 2.1, which may vary in different books and different as it varies with the temperature. So the values may be a little deviated as compared to the Mollier chart as well as from the other books. So T superheated from this calculation comes to be 503.906 Kelvin and 230.906 in degrees Celsius. So this is T2 and the condition at 2 is also found to be superheated. Now to find the enthalpy, we will use the formula for the enthalpy of superheated steam, which is Hg plus Cp of superheated steam into T superheated minus T saturated. Then again, to find the Hg at 8.73 bar, we again have to use the interpolation in this similar way and we obtain Hg at 8.73 bar as this one. So now H2 we will calculate by putting the Hg Cp Ss at as 2.1. Superheated temperature of superheat we have already calculated as 230 and T saturated we have already calculated as 174 above. So H2 is obtained to be 2890.1246 kilojoules per kg. Now to find the specific volume at point 2, we are using V upon T is equal to constant. So this is V2 upon T2 is equal to Vg upon Tg. Vg upon Tg at 8.73 bar. For that we need Vg. Vg at 8.73 bar will again be done by using the interpolation. So this is coming to be 0.22365 meter cube per kg. Fine. So this is Vg and Tg we already know, but I have put it in Kelvin plus 273. Fine. Whatever the temperature in degrees Celsius plus 273. Then T2. T2 we have already calculated as this. And in Kelvin it is 503.906. So we have put T2, we have put Vg, we have put Tg and we obtain the V2. That means the specific volume at point 2. So we obtain it as this one. Now for the point 3. Point 3 is which point? It is this one. Fine. And it is the exit condition. The pressure for it is given as 5 bar. So at 5 bar will not need interpolation further. So it will be Sg is 6.819 and the S1 is equal to S3 was found to be 6.88. So comparing these, we find that the condition at 3 is also superheated. So using the same formula as for the superheated steam, we have to find the temperature of superheat at point 3. So putting all this in a similar manner, Sg, then T saturated is found to be at 5 bar. It is found to be 151.8 degrees Celsius plus 273 for conversion into Kelvin. And this is S1 which is equal to S3. Obviously it is an isentropic process. So this is giving the T superheated at point 3 as 438.24 Kelvin, which is equal to 165.24 degree Celsius. Now for having the enthalpy at this point or point 3, we will have Hg plus Cp of superheated steam. The formula for superheated steam of the enthalpy for superheated steam, it is this one. So H3 is now this. Now to find the specific volume at point 3, again the same formula. So V3 upon T3, Vg upon Tg, then Vg upon Tg is this at 5 bar, and V3 upon T3 is, right now we have calculated T3 in Kelvin. So this is V3 is equal to 0.3865 meter cube per kg. Now we have been given two conditions in the question, which is neglecting the friction and considering the friction. So now by now we have calculated the factors, and now we are going to calculate whatever is asked in the question. For that, condition 1 is neglecting the friction. So neglecting the friction, we will find C2. C2 is equal to under root of 2H1 minus H2, and this 1000 is for conversion of this kilojoules into joules. So we get C2 is equal to 537.91 meter per second. Now mass flow rate is given as 1 kg per second, and mass flow rate is given by rho AC, and it may also be written as AC upon specific volume. So for the point 2, A2 C2 upon V2 can be written, and A2 can be isolated and others can be taken on the right hand side, which gives m dot upon V2 upon C2. So m dot is 1, V2 we have already calculated, then C2 we have already calculated. When we will put this, we will get the A2 as this one. So C2 we have obtained and A2 we have obtained. This is neglecting the friction. Now at exit it will be C3, and C3 will be under root of 2 H1 minus H3, because it is about the exit condition. So it will be H1 minus H3 into 1000 for conversion into kilojoules, kilojoules into joules. So C3 is obtained as this. Then m dot is again A3 C3 upon V3, as we have equated it once. Then A3 is given by this m dot into V3 upon C3. So m dot into V3 we have calculated upon upon C3 is 719, we have just calculated. So we obtain the area at exit as this. Now the second condition is considering the friction. So considering the friction, what will change will be the enthalpy drop, and it is given that we have to consider the friction loss of 10% throughout the nozzle. So for 10%, the efficiency will come out to be 90%, as 10% is lost, rest of the 90% will be used. So the actual heat drop which will be useful will be 0.9 into H1 minus H2, which will be equal to H1 minus H2 dash. So C2 dash will be equal to, this is the modified formula for the C2 dash, which will be the actual velocity with while considering the friction. So it will be 2 into H1 minus H2 dash into 1000 on H1 minus H2 dash will be equal to 0.9 into H1 minus H2. So this will be the, this is just put as H1 minus H2 only and into 0.9 kiya to account for the friction, and we get C2 dash is equal to 510.31. Now for obtaining the A2, that means the area at exit while considering friction, it will be, we will be using the same formula, and this formula gives A2 is equal to this one. This is with the C2 dash, not with C2. So for the exit also we will use the similar way. So actual heat drop will be 0.9 into H1 minus H3, which will be equal to H1 minus H3 dash, and putting this in the formula for C, it will be C3 dash is equal to this. Now we will obtain C3 dash in a similar fashion, and then for calculating the A3, so A3 will be 5.66 into 10 to the power minus 4 in the similar way as we have obtained A3. So this is the numerical covering with and without friction conditions in a nozzle to find the velocity and area at the exit. While we have the other relevant data, different types of questions can be extracted from this one only, and later we'll discuss a different type of numerical too. Thank you so much.